41ページあたりから始めます。ここからいきます。Thermal property of the free electron gas. Fermi-Dirac distribution. When the temperature is not zero, it is necessary to examine the excited states of the n-electron system as well as its ground state. According to the basic principles of statistical mechanics, if an n-particle system is in thermal equilibrium at temperature T, then its properties should be calculated by averaging over all n-particle stationary states, assigning to each state of energy E with a weight Pne proportional to exponential minus E divided by kBt. Assigning states of energy E with weight. I don't think this is not so precise. I would say this is not so precise. Here, E sub alpha n is the energy of the alpha's stationary state of the n-electron system, the sum being over all such states. I think here, if this is a degenerate, if there is a degeneracy, you can just label alpha 1 if this is degeneracy, alpha 2 if there are degeneracies, you can put number, unique number for each degenerate state. So then I think this averaging procedure works. The denominator of 238 is known as the partition function and is related to the Helmholtz free energy F equal U minus Ts, where U is the internal energy and S the entropy, by partition function is equal to exponential minus Fn divided by kBt. We can therefore write 238 more compactly as Pn of E equal exponential minus E minus Fn close bracket divided by kBt. Because of the exclusion principle, to construct an n-electron state, one must fill n different 1-electron levels. Thus, each n-electron stationary state, each n-electron stationary state can be specified by listing which of the n1 electron levels are filled in that state. A very useful quantity to know is F sub I n, the probability of there being an electron in the particular one electron level I when the n electron system is in thermal equilibrium. In the case we are interested in the level I is specified by in the case we are interested in the level I, in the case we are interested in the level I, there is a comma. In the case we are interested in the level I is specified by the electron's wave vector k and the proportional projection s of its spin along some axis. This probability is simply the sum of the independent probabilities of finding. This probability is simply sum of the independent probabilities of finding the n electron system in any one of those n electron states in which one of those n electron system in which the ith level is occupied. F sub I n equals summation Pn of E alpha n, summation over all n electron states alpha in which there is an electron in the one electron level I. We can evaluate F sub I of n by the following three observations. Number one, since the probability of an electron being in the level I is just 1 minus the probability of no electron being in the level I, those being the only two possibilities allowed by the exclusion principle, we could equally well write 241 as F sub I n equal 1 minus summation Pn of E gamma n, summation over all n electron states gamma in which there is no electron in the one electron level I. By taking any n plus 1 electron state in which there is a by taking any n plus 1 electron state in which there is a electron in the one electron level I, we can construct an electron state in which there is no electron in the level I by simply removing the electron in the ice level, leaving the occupation of all the other levels unaltered. Furthermore, any n-electron state with no electron in the 1 electron level I can be so constructed from just 1 plus L plus 1 electron state with an electron in the level I. I think these two things are saying the same thing. Interesting. This part. By taking L plus 1 electron system, we can construct n electron system any n electron system with no electron in 1 electron system can be so constructed from just 1 n plus I think this is saying the same thing. Okay. 18. Namely, the one obtained by occupying all these levels occupied in the L electron state plus the I level. Namely, one obtained by occupying all those levels occupied in the n electron state plus the ice level. I don't understand. Furthermore, any electron state with no electron in the 1 electron level I can be so constructed from just one obtained by occupying all those levels hard to understand this. Evidently, the energy of any electron state and the corresponding n plus 1 electron state differ Why is this any electron system may have level I already occupied. the energy of the only one electron level whose occupation is different in two states. I want to understand what exactly he want to say. By taking any 1 plus 1 n plus 1 electron state in which there is an electron in the one electron level I, we can construct an n electron state in which there is no electron in the level I by simply removing the electron in the ith level, leaving the occupation of all other levels unaltered. This is okay. So I say this is okay. Furthermore, why furthermore? Any n electron state with no electron in the one electron level I can be so constructed from just one n plus 1 electron state with the electron in the level I. I think it's saying the same thing as before. I don't know why he says same thing again. Same. Evidently, the energy of any n electron state why any? And the corresponding n plus 1 electron state differ by just EI, epsilon I. The energy of the only one electron level whose occupation is different in the two states. Thus, the set of energies of all n electron states with the level I unoccupied is the same as the set of energies of all n plus 1 electron states with the level I occupied, provided that each energy in the latter set is reduced by epsilon I. Okay. We can therefore rewrite 242 in the peculiar form. Okay. So here, okay, so gamma is changed alpha. Yeah. So here. This one was before gamma, is now alpha. That means occupied. But then we minus this. Summation over all n plus 1 electron states alpha in which there is an electron in the 1 electron level I. But equation 240 permits us to write the summand as Pn of something like this is so I have some have some memo here. So this part is exponential minus e alpha n plus 1 minus epsilon I minus f n plus 1 divided by kBt. Then okay. So if we put epsilon I outside, so if I put this epsilon I outside, the thing left over is this one. Then mu is this. Mu is this. So I think this thing will cancel this one. Yeah, I think so. See? This is more like this. This thing is more like exponential minus Fn. I think it's very important to repeat this as an exercise. So this didn't work. This didn't work. Oh, this didn't work. Fin. This is 1 minus summation Pn then E alpha n plus 1 but epsilon I is subtracted. Then we can Pn E alpha n plus 1 epsilon I subtracted. This is actually why this is Pn plus 1? I think this is because this is Pn. So this is more like this. E to the minus E alpha n plus 1 minus epsilon I minus Fn. Is it upstairs? F downstairs. Divided by kBt. Let me see. Is this n plus 1? Yeah, and this is equal E minus E alpha n plus 1 minus epsilon I minus F n plus F n plus 1 divided by kb t e to minus f n plus 1 kbt equal exponential epsilon I minus fn plus 1 minus fn minus fn kbt exponential minus this is plus exponential E alpha n plus 1 minus f n minus n plus 1 kbp. Is it correct? E minus f. Okay, this is correct. So this part is P n plus 1 E alpha n plus 1. Then this is called mu. Yeah, okay, I think I derived this. Where mu, known as the chemical potential, is given at temperature T by mu equal f of n plus 1 minus f of n. Substituting this into 243, we find one minus exponential epsilon I minus mu kbt summation of over all n plus 1 electron states alpha in which there is an electron in the 1 electron level I. I think this is okay. Comparing the summation in 246 with that 241, one finds that 246 simply asserts that Fin equal minus 1 minus something Fin plus 1. Interesting, but it's a little complicated. Equation 247 gives an exact relation between the probability of the 1 electron level I be occupied at temperature T in n electron system and in n plus 1 electron system when n is very large, and we are typically interested in n of order of 10 to 22. It is absurd to imagine that by the addition of a single extra electron could appreciably alter this probability for more than insignificant handful of one electron levels. 19. For a typical level, changing n by 1 alters the probability of occupation by order 1 over n. See problem 4. We may therefore replace fin plus 1 by fin in 247. Then we replace this one to fi of n. Which makes it possible to solve for fin. In subsequent formulas, we shall drop the explicit reference to the n-dependence of Fi, which is, in any event, carried through the chemical potential mu. C. 245 245 The value of n can always be occupied can always be computed given the Fi by noting that Fi is the mean number of electrons in the one electron level. Mean number of electrons in the one electron level I. Proof. A level can contain either 0 or 1 electron, more than one being prohibited by the exclusion principle. The mean number of electrons is therefore 1 times the probability of 1 electron plus 0 times the probability of 0 electrons. Thus, the mean number of electrons in the level is numerically equal to the probability of its being occupied. Note that this would not be so if multiple occupation of levels were permitted. Since the total number of electrons n is just the sum over all levels of the mean number in each level. N equals summation over I, f of f sub I equals summation over I, 1 over something, which determines N as a function of temperature T and chemical potential mu. In many applications, however, it is the temperature and N, or rather the density N equal capital N over capital V that are given. In such cases, 249 is used to determine the chemical potential mu as a function of N and T, permitting it to be eliminated from subsequent formulas in favor of the temperature and density. In such cases, 249 is used to determine the chemical potential mu as a function of N and T, permitting it to be eliminated from subsequent formulas in favor of temperature and density. However, the chemical potential is of considerable thermodynamic interest in its own right. Some of its important properties are summarized in Appendix B, 21. The chemical potential plays a more fundamental role when the distribution 248 is derived in the grand canonical ensemble. For example, life, statistical and thermal physics, our somewhat unorthodox derivation, which can also be found in life, uses only the canonical ensemble. Yes. Maybe shall I stop here? Too long. So this is again 42. Okay, 42. See you.